Hello. Recently I'm receiving a decent number of email messages and forum questions like do you need LNA or where should I put the filter and how the filter will affect my noise figure and overall system performance. So I decided to explain a few simple things regarding the low noise amplifier and how the LNA can improve your signal to noise ratio. So mainly the guys are interested in the L-band operation, and L-band is covering from 1 to 2 gigahertz. So both Inmarsat, Turaya, Iridium, and also Meteosat on 1.7 gigahertz is well within the L-band. So let's take for example 1.7 gigahertz. The L-band Meteosat frequency. And we will take the standard setup where we have the dish antenna, for the 1.7 gigahertz. And we have connected straight to the feed widely used, let's say, DVB-T dongle with R820T or 2 dongle. What we are looking is the system temperature using the antenna and the dongle. So TS is equal antenna temperature plus receiver temperature. Properly designed antenna should see just the sky. So mainly the temperature of antenna is dictated by the temperature of the sky the antenna sees. If the antenna is properly designed, this means that the feed is properly designed to not to have a spillover. Otherwise we will see the hot ground, and the temperature of the ground is 290 degrees Kelvin. It's much better to have under illuminated antenna, so to have less gain in reception rather than spillover and to take the noise temperature. So the average noise temperature on 1.7 gigahertz for the elevation, let's say 45 degrees, it's 55 degrees Kelvin. So TA, it's 55 degrees Kelvin. TR is actually the noise figure of the dongle. Usually noise figure of the R820T or T2 is 6 dB. 6 dB is corresponding to 864 degrees Kelvin. 864 degrees Kelvin. So system temperature is 55 plus 864, 919 degrees Kelvin. Okay, so this is the first situation, the standard one, when we have the dongle straight to the feed. Let's now analyze the same system, so the same antenna with the same feed. but in this case we will first have LNA, and then the LNA will be followed with our R820T dongle. And we are looking for the system temperature. Again, TA plus TR. TA, we already found that the antenna temperature is 55 degrees Kelvin. And we need to find out now the receiver. Now the receiver, we need to calculate the temperature of the receiver. It means LNA and the dongle. For that we will use the Fries formula for the noise temperature. And the Fries formula goes like this: T, so TR in this case is equal T LNA plus T R820T divided by gain of the LNA. Okay, let's use the LNA for all. Noise figure at 1.7 gigahertz. It's approximately 1 dB, and the gain is 16 dB. So this is a gain, and this is noise figure. 1 dB converted to the temperature, it's 75 Kelvin degrees. 75 degrees Kelvin, and 16 dB in power ratio, so this is 40. 20 dB is 100, 70 dB is 15, 16 dB is 40. Now we have everything to calculate receiver temperature, TR. TLNA, it's 75 plus dongle temperature, we found out it's 864 divided by 40. So from here we can see that the influence on the receiver temperature or complete noise figure depending mainly on the first stage, so the noise figure of the LNA, and the gain of the same first stage, as the second stage is divided noise figure by the gain of the first stage. So we would like to have a lower noise figure as possible and a higher gain as possible. So this is 75 plus 864 by 40. 864 divided by 40. 21.6. This is 96.6 degrees Kelvin. So if we convert that in decibels, 96, okay, 101 is 1.3 dB. So roughly, noise figure is 1.3 dB. So adding the low noise amplifier before the dongle, we decrease the noise figure from 6 dB to 1.3 dB. So the difference is 4.7. So how does this affect our reception, our signal to noise ratio? Now we can calculate signal to noise by 10 logarithm base 10 of TS without LNA, so 919 divided by TS with the LNA. So TS is TR plus TR. It's 55 plus 96.6 Kelvin. And this is 151.6 degrees. So 91919 divided by 159.6. 919 divided by 151.6. 606. Now we need to do the logarithm. It's 0.7824, and we need to multiply this by 10. So 10 by 0.7824, and we have the signal to noise ratio 7.824 dB. Okay, now we have everything calculated. We decrease our noise figure from 6 to 1.3, so the difference is 4.7 dB. We improve our noise figure, and 4.7 dB give us better signal to noise ratio for any signal on 1.7 gigs, 7.8 dB. At the end, this is how much we will improve our reception. Signal to noise will be better for the 7.8 dB using the same antenna, just adding the low noise preamplifier. So that's it. Thank you. 984 Queen Victor.